Hello everyone. Lab number 4 will cover the topics of extraction and sublimation. More information on this topic can be found in the textbook in section 9, pages 103 to 121, and section 8.3, pages 97 to 98. First off, we must answer the question of what is extraction? Previously, we performed two purification techniques, one for solids and one for liquids. However, each of the compounds used were obtained from previously isolated sources. Extraction is a technique used to isolate desired organic compounds from other unwanted impurities. This process often utilizes a chemical's solubility and/or acid-base properties. Extraction is a common technique used to isolate secondary metabolites from raw plant material in an effort towards isolating interesting and unique natural products. Pictured to the right is an example of a molecule that, despite its complex structure, was able to be extracted from a plant using common solvent ethanol. As one of the last steps in this week's experiment, we will be investigating the concept of sublimation. Sublimation describes a phase change whereby a solid passes directly into the vapor phase without going through an intermediate liquid phase. Sublimation can be used as another purification technique. However, it is only applicable for select solids which have an appreciable vapor pressure below their melting point. The hydrocarbon adamantane is a white solid with a camphor-like odor which readily sublimes under normal atmospheric pressure and temperature. Though adamantane itself does not provide any useful therapeutic effects on its own, it is used as a derivative in a number of other antiviral medications. In this lab, we will be working to isolate and purify the commonly used psychoactive substance of caffeine from black tea. Though technically considered a pesticide, when ingested, caffeine acts as a stimulant, causing increased alertness and an elevated heart rate for the user. Caffeine has a number of interesting physical properties which we will utilize in this lab, including being moderately soluble in water at room temperature, having increased solubility in boiling water, and being very soluble in organic solvents such as dichloromethane. Though we are most interested in caffeine, we must contend with a slew of other soluble and insoluble impurities. Let's look at how a solid-liquid extraction works. Tea leaves contain other unwanted organic compounds, mainly dark-colored tannins and undesired solids, mainly comprised of cellulose. Thus, to separate the caffeine from the tea leaves, we will first perform a solid-liquid extraction. Most people are quite familiar with such extractions, since we are simply brewing our tea in hot water. However, for this experiment, we must alter the pH of our solution to account for unwanted impurities. Another form of extraction is liquid-liquid extraction. A liquid-liquid extraction is a common laboratory procedure used to isolate a desired compound from other similar chemicals. This is typically performed using a separatory funnel. Pictured to the right is a separatory funnel sitting in a ring clamp connected to a ring stand. At the top of the funnel is a stopper to close the funnel, and at the bottom is a stopcock to open the funnel. The stopcock is used to drain the denser liquid when performing an extraction. Commonly, your desired compound will be soluble in either an organic phase or an aqueous phase, where the organic phase is comprised of organic solvents such as dichloromethane, ethyl acetate, etc., and the aqueous phase is pH-adjusted water, acidified with ammonium chloride or basified using sodium carbonate. In this experiment, we will use dichloromethane as our organic layer to separate caffeine from the sodium salt of gallic acid. Dichloromethane is a dense, halogenated solvent that readily dissolves many organic materials. One of the major impurities we must deal with are tannins. Tannins are large, polyphenolic compounds which impart a brown color to tea. When hydrolyzed or broken apart in boiling water, tannins produce glucose and gallic acid. As the free acid, gallic acid is only partially soluble in water. We can increase the solubility of our unwanted impurity, gallic acid, by adding base. Using sodium carbonate, we form the conjugate base of this impurity, ensuring its solubility in water. When we do so, sodium carbonate turns into carbonic acid, which then forms an equilibrium with water, producing CO2 gas. Another impurity in our experiment is cellulose. Cellulose is the main solid constituent in leaves and paper and is comprised of polysaccharides. Polysaccharides are simply monosaccharides chained together to give one large molecule. The monosaccharide used to make cellulose is glucose. For our experiment, cellulose is considered an insoluble impurity. So, from our initial solid-liquid extraction of tea leaves, we must be able to handle the following four compounds. First, caffeine, our desired compound, will be dissolved in the hot water we use to brew the tea. Next, we will also expect to extract out of the leaves the dark tannins. These tannins will be broken down and turned into the sodium salt of gallic acid and glucose, both of which are water-soluble impurities. Finally, the leaves and the bags from the tea are unwanted cellulose products and are not water-soluble impurities. So, to recap, we will perform 5 steps in the lab in an effort to isolate pure caffeine from tea leaves. The first step involves a solid-liquid extraction, giving an aqueous mixture of caffeine, cellulose, and tannins. Next, we will perform a vacuum filtration to remove any and all solid impurities from our solution. The filtrate collected will then be subjected to a liquid-liquid extraction as step number 3 in our experiment. The product obtained from step 3 will then be dried, gravity filtered, then evaporated of any organic solvent, step number 4, giving impure caffeine solids. Finally, the impure solid will be sublimed in step number 5, giving purified caffeine crystals. Step 1 for the laboratory procedure involves brewing the tea. Thus, obtain one 250 milliliter beaker and place it on a hot plate. To this, add 2 grams of sodium carbonate and 100 milliliters of deionized water. Stir this to dissolve the solid. Then, add 5 tea bags to the beaker. Set the hot plate to 80% and boil the water for 20 minutes. If lots of water vaporizes, maintain the water level between 75 to 100 milliliters by adding additional water. Once your tea is done steeping, you must perform a vacuum filtration. Perform a vacuum filtration setup as depicted. Make sure to clamp your filter flask, use the right-sized rubber sleeve, use the right-sized filter paper, pre-wet the filter paper, and be sure to use one of the thicker black hoses for the vacuum line. Turn on the vacuum knob on the fume hood and perform the filtration. Then, using a spatula, you may press the tea bags on the Buchner funnel to collect as much filtrate as possible. This filtrate is your aqueous phase. In this next step, you will perform a liquid-liquid extraction of your filtrate. To a 125 milliliter separatory funnel, ensure that your stopcock is closed, then add your brown filtrate to the funnel. Next, add 10 milliliters of fresh dichloromethane. The DCM will be your organic phase for this experiment. Next, affix a glass stopper to the top of the funnel and gently swirl the contents for about 10 seconds. Stop swirling and place the funnel in the ring clamp on the ring stand. Allow the solution to sit undisturbed for a few minutes on the clamp. This should allow the aqueous and organic phases to separate into 2 layers, giving a visible bilayer in your funnel. Once the bilayer becomes visible, drain the colorless bottom DCM layer into a 100 milliliter or larger beaker. Once you have collected your organic phase in a separate beaker, repeat the experiment 3 more times, with each time using 10 milliliters of DCM. Be careful when draining the DCM layer. You should leave a little bit of DCM layer in the set funnel to prevent any aqueous layer from entering the beaker. Also, when swirling your solution, do not shake the funnel vigorously, as this will likely cause the formation of an emulsion. After 4 liquid-liquid extractions, all of your caffeine will have been extracted from the aqueous phase into the DCM organic phase, since caffeine is more soluble in DCM than water. In step number 4, you must dry your organic layer of any trace amounts of water by adding about 3 grams of anhydrous magnesium sulfate directly to your DCM solution. Once added, you will remove any clumps of magnesium sulfate by performing a gravity filtration. This is performed by pouring your organic layer through a fluted filter paper and glass funnel. The filtrate is collected in an Erlenmeyer flask and kept for the next step. Note that if you happen to drop some brown aqueous layer into your DCM solution by accident, you must remove any large droplets of water using a pipette before adding magnesium sulfate. For the following steps, you will need 2 beakers, 1 small beaker and 1 large beaker. These beakers, however, must satisfy the following condition. The small beaker must hang inside of the large beaker and give a 1/2 inch gap of space between the beakers. This will be required for the sublimation step. Transfer your dried DCM solution to a large beaker and place it on a hot plate. Next, dial in the heat on the hot plate to 50% and allow all of the DCM solvent in your solution to evaporate completely, leaving behind impure crystals of caffeine. For this last step, with your large beaker on the hot plate, turn up the heat to just below 100% and evaporate your compound until dryness. Take the small beaker and fill it to the brim with ice and 10 milliliters of tap water. Thoroughly wipe the bottom of the smaller beaker with a paper towel and carefully drop the small beaker into the large beaker. It should have a 1/2 inch gap between the 2 beakers. At this point, hot vapors of sublimed caffeine should start to be seen collecting on the bottom of the small beaker. By using a cold beaker, the major problem in sublimation is moisture condensing outside of the small beaker. The best way to avoid this problem is to make sure that the solid is completely dry and the hot plate is hot enough so that caffeine vapors adhere quickly to the dried smaller beaker. While performing the experiment, make sure you wipe off any additional water droplets from your beaker. Once you see caffeine crystals forming on the small beaker, you should scrape off any collected crystals of caffeine onto a tiered or pre-weighed watch glass. Weigh your sample of purified solid to find the mass obtained. Depending on time, your TA may ask you to characterize your compound via melting point. At the end of the experiment, used tea bags and filter paper should be placed in the solid waste. Any unused dichloromethane should go in the halogenated waste. Broken glassware must be placed in the glass waste receptacle, and any remaining aqueous phase should go in the aqueous waste. And that's the end of another lab. Thanks for your attention.